Hello, my name is Evan Hennis, and this video will cover a project I created that uses binary classification using TensorFlow and Keras. This video will have a quick introduction of binary classification. I'll then go on to talk about the creation of a neural network and finally show how I put all of them together to help predict a football play based on a set of input parameters. The goal of my demo project is to predict the next play call based on the down, the distance, and the quarter. A plot at 1 means 100% chance of run. A plot at 0.5 means it's 50% run, 50% pass. A plot at 0 means it's 0% of run or 100% chance of pass. Along the x-axis is the distance from the first down. 5 means there are 5 yards to gain. 10 means there's 10 yards to gain. Each graph is broken into one of 4 possible downs. If you've been paying attention, I mentioned that I also used a quarter as an input variable. These are shown based on the colors of the dots. Binary classification is described as classifying your data into one of 2 groups. In my demo, I am trying to classify a run or a pass play. I use a single output value, so anything above 1/2 is run, anything below is a pass. Now, it should be noted that typically you would have only a 0 or 1, but I'm using the confidence level as well. I will now show my demo of Football Scout in a Jupyter notebook. This is my Jupyter notebook that will demonstrate the binary classification using TensorFlow and Keras. I have a CSV file with around 430 plays across 8 games in it. For my includes, I'm including pandas, numpy, pyplot, and I'm also ignoring some warnings. Here, I'm using pandas to load the CSV file with all the plays. And here's a peek at the top 5 rows. The next few sections are just getting a look at the data and doing some general statistical analysis. Here's where I check to see how many of the plays are runs versus passes. As you can see, there's 202 runs and 225 passes. If there are any math majors out there, you can see that we are short a few plays. Those are penalties. Eventually I'll need to convert the run-pass column to an integer for my model, so I'll do it here. In this box, I'm graphing all the plays in the same format as I showed in the PowerPoint, but here I'm using the percentage of run-pass for a certain down and distance. One thing you'll notice is not every distance has a play. This is a limitation to statistical analysis. Now that the statistical analysis part is done, we can go through the meat of this video, the machine learning. I imported a few methods to customize my training, which you will see later. I'm also importing Seaborn for a pair plot method. In this case, it doesn't return much, but I do recommend using it for larger data sets. I also grabbed TensorFlow and Keras. Here I'm reloading the data set, so I don't have to worry about any changes I made up above in the statistical analysis. With my current data set, I won't have to do anything extra after I one-hot encode the run column. But remember, if there were a lot of nulls or NAs, I would have to handle that here. You have to remember, though, that anything you change, it will impact how you're training. Don't introduce any biases by your actions. Here are the results of the pair plot. As I said earlier, it doesn't show much in this certain breakdown, but doing a graph like this will give you a little bit of data about how your data lines up with the rest of your values. I like to split my data sets 80-20 between training and testing. It gives me plenty of training data, but it still leaves me plenty of data to test to validate my model. Here I create the stats table for the normalization I do later. Here I remove the results or labels from the training and test data set. When working with numerical data, you need to normalize your numbers. Without normalization, one of your columns can have an outsized effect on your training just because of the magnitude of its range. Now, here's the important part. Here's the model that I found worked the best for my data. All of this will vary based on the data you have and how much training is needed. I use a Keras sequential model since it will run each layer one at a time. I've done 3 dense layers, 2 with 64 nodes, and my output layer with 1. I'm using ReLU for the activation in the first layer. The input shape is the length of my training keys, and in my case it's 3 things. It's down, distance, and quarter. And finally, your last layer is dense of 1. That's because I'm doing the binary classification. Using the confidence level, I only return 1 value. And in order to make this from 0 to 1 like I need it, I need to use the softmax activation. For the optimizer, I'm using Atom. It's kind of the standard go-to optimizer. If you have certain data, different optimizers work a little better. They train a little quicker. But for my project, Atom did just as good. And then I come down to the compile part of my model. I'm using mean squared error for the loss function, optimizer's Atom as listed above. And the metrics I return are accuracy, mean absolute error, and mean squared error. So here I set the model. And here's where I use the custom method, the print doc. Typically this prints out a ton of data. I didn't need that in this situation. So for me, every 100 epochs, I return just a period. And here's the actual training of the model. I'm using normalized training data, the training labels that match those. Epochs is 30 is the iterations on training. Validation split is 20% of my training data. Verbose is 0 because I don't need to see all the information. And then my callbacks to print documents. And here's my training output. In this section, I turn this history return into a data frame, and I add the epochs to it. And here's the last couple rows. It shows the value lost, the validation accuracy, validation mean absolute error, mean squared error. And these are the training returns, loss, accuracy, mean absolute. And the important stuff, the actual model evaluate. In this case, I got just under 61% accuracy. A lot of demos you'll see in the 90s, but a system like this, 60 is not too bad. I have a model I've saved that's at 68%, and we'll use that for our graphs. And here's everything in one section. Build the model, fit, and then do my testing. What you'll notice is epochs is 200 here. I want to run a few more times. In this case, you notice with the 200 runs, I do start to overfit a little bit as I drop down to 56%. One of the things to watch out for in a neural network is that the more you run the data, you will overfit to that data. And here's the section of the output. A model's nothing if you don't have something good to show your users. This is the actual implementation of it. So here I do a simple model.predict, and then I create an NumPy array of my 3 input values. Now I'm just doing first and 10 over 4 quarters, second and 10 over 4 quarters, third and 10 over 4 quarters. And if you look at this, 89% of the time, the neural network says you're going to run on first and 10. And if you look, they're all pretty close all the way through. And here is the graph I did in the PowerPoint. It'll look different than ours because this isn't my saved model. But you can see I do the same thing as above. I do the predict on the 3 types, the 3 input values, and then I plot that. And you'll see that I plot for first, second, third, and fourth down, add some space in the layout, and here's what you get. As I mentioned earlier, I do have a saved model. And in that case, you just do your model.save with your name, and this saves everything. There are other ways to save, so you should look in to see what you actually want to do, but this one worked best for me. So to wrap up my demo, I'm going to use my good model I'm going to load. And that's simple, called a Keras models.load with my data I saved. I do have to recompile, and I'm doing binary cross entropy, Atom optimizer, and the same 3 accuracy, or the same 3 metrics returned. As you can see, after all of this work, I do get up almost 86%. As listed above, I'm going to plot this, and you'll see the graph I showed in my PowerPoint with the first, second, third, and fourth downs, the distance, and then the percentage of run. And just to clean everything up, here are the raw numbers for each of the entries. Now I hope this has been of some use at some point during my video. I walked you through creating a neural network using the libraries Keras and TensorFlow. I created a binary classification solution. And I finally gave the users something they can see. And that's the most important part, making sure your users are happy. Thank you for watching this video. I hope to make a few more. Thank you.